Oh gosh. Okay, so we've done minimum and maximum values on parabolas, on polynomials, on quadratics, etc. Now, if you had a cubic function, let's say, and it looked like this. This is a maximum, and this is a minimum, but we would refer to them as actually relative maxes and relative mins, because that's not the absolute highest the graph goes or the absolute lowest, correct? So your maximums and minimums are either relative or they're absolute. This would be a relative max, and this would be a relative min. Okay? At those points, we've discussed this before, at those points, what would your slope of a tangent line be at those points? What's straight? Not one. Yeah. They would have slope of 0. So the m tan would equal 0, correct? How do we find the slope of the tangent? Which derivative? The first derivative. So if we find the first derivative of any equation that I give you, and you set them equal to 0 and solve for x, you're going to find every spot where the tangent is either 0, or you could end up with an actual vertical line. It's going to be where the critical numbers exist. It's where you're going to find your maxes and your mins. Okay? Or you could find technically asymptotes as well. So we're going to just find critical numbers. So the easiest way to find critical numbers, I guess the only way to find critical numbers, we're finding the critical numbers of the first derivative. And the critical numbers of the first derivative are going to help us get the maxes and mins, because that will be when the m tangent is 0, right? When m tangent is 0 is when you're going to get those max and min. Relative, just lazy, REL. Relative max and relative min, because they're not the highest. Whereas if you had a graph like this, this would be a relative max, relative min, absolute max. So that would be an absolute. So we're going to find critical numbers first before we even do any discussions as to how to find if it's a max or a min, or if it's just a critical number that tells you that the graph does something else. Okay? But we're going to solve for critical numbers. The way we solve for critical numbers of the first derivative, is we are going to find the first derivative, set it equal to 0, and solve for the x values. Okay? So we're going to find the first derivative. Then we have to solve the first derivative. So that's either going to be like, we might have to factor parts of it. We might have to GCF parts of it. We might just be able to take the numerator and the denominator and just find out what the critical numbers are. But the critical numbers come from both the top and the bottom of the first derivative. Then we're going to solve for x. Should we find the first derivative set equal? So the hardest part of this is actually going to be finding the derivative, right? So that's why I said to you, if you couldn't do last unit, this unit's impossible. Because if you can't find the derivative of something, how do we even solve it? We can't. We're going to have the wrong derivative. So we'll look at some basic ones first, some polynomial ones first, because polynomials use power rule, right? So that's a lot easier. But we're going to have to be able to solve polynomials then as well. So let's look at an example. Find the Find the critical numbers of A. So we're just going to look at a polynomial. F of x equals x cubed plus 6x squared minus 15x. Okay? In order to find the critical numbers, we have to do the first derivative. So we're going to do f prime of x. This one's easy. It's just power rule. Take the 3, drop it in front. X to the 2. Plus take the 2, drop it in front. 6, x to the 1. And then minus 15. So f prime of x is 3x squared plus 12x minus 15. And then set it equal to 0. So this is just solving polynomials again, or solving quadratics from grade 11. This particular question. How do I solve for x when it's 3x squared plus 12x minus 15? You can factor it. What's a quicker way to do it first so that I don't have to do decomp? Just in this particular case. Take out a 3. So I get 0. I get a 3 out here. And then I get x squared plus 4x minus 5. You could have left the 3 and done decomp. You'd be just fine. You'd still end up pulling the 3 out at the end. So now I say, what times what equals negative 5? What plus what equals positive 4? Positive 5, negative 1. And because there's a 1 in front of this x squared, I can just put brackets. I don't have to do decomposition. So I'm going to get x plus 5 and x minus 1. Does the 3 in front get me a critical number? When you have that 3 in front, does it get you anything? No, because it doesn't have an x with it. Okay? But the other ones do. So we're going to go x plus 5 equals 0. X minus 1 equals 0. So x equals negative 5. And x equals 1. Now we're going to look and see what the critical numbers actually do for all the cases that we're going to look at for the next few examples, okay? So if you have a graphing calculator still, you're going to take it out just to see this. You're not actually going to have it for the test. But I want you to see what these critical numbers, what these x values do, and I'm making you pull yours out because mine is frozen and it won't work. Let's see, maybe today it will. Oops. Okay, so we're going to look at the original graph, correct? At x equals negative 5, what's occurring? At x equals negative 5, what's occurring? Is it? Or is it a minimum? What is it? It's just a line. Of the original or the...
X equals negative 5. I thought you meant y equals 5.
No, x equals negative 5. When x equals negative 5, you have a maximum. When x equals 1, what do you have? A minimum. I really wish I could pull my calculator up. This is so much more intriguing. So now into y2, type in your derivative. Don't clear out your y1. Just in y2, type in your derivative. And make the line thicker if you don't have colors, which majority of you won't. Some of them do. Just, I think only Cole has it.
Well, is it your cheating? No, it's this one.
There's so many options. Okay, so, or make it thicker. Does everyone know how to make the line thicker? Did I teach you how? I can't remember. Go to the very left and hit enter once. Very, very far, enter, graph. So at least you know which graph is which. Okay. Your first derivative tells you what your tangent slope would be, correct? So If you look at your first derivative, your first derivative, if you look, your graph is actually decreasing along that first derivative and increasing along this second part. It's where you're going to see your change in increase to decrease. I wish I could show it on the board, but I can't, so it'll be a tomorrow thing. Okay. So do you see how this is the critical numbers, though, where at least we have maxes and mins occurring? Yes. How? So your calculator's taken away, right? I'm not letting you have it for the test. So for those of you who are going second trace max, left bound, right bound, enter to get the y, to get the maximum, to prove that this was a maximum, right? I took away your calculator. You know, though, that this is a max and a min. I'll show you through tables how you can tell if it's a max or a min, because right now you could tell because I made you pull up the calculator, right? But until I teach you that, how could you get the actual point, though? Right now I have the x values. No, but I want you to get the what? You could plug in the x into what? Into the original equation. You want the y of, you want the max and the min of the original equation, right? So we got the x values of the original by using the first derivative. To get the y values, you're going to plug them back into the original. Some people try and plug them back into the first derivative. Don't do that. That's not going to get you the actual y value. It'll get you a y value of 0 because that's what you just found, right? It's not going to help you out there. Okay? So if you look at your first derivative, though, guys, look at your first derivative graph. Take out the other one. Take out your y1. Just look at the first derivative graph. Yeah, you should have a quadratic because it's just the quadratic, right? It's just the parabola. What's negative 5 and 1 now on that graph? The x-intercepts, correct? Why is it the x-intercepts? Well, we found it as being the x-intercepts, did we not? Now, what part of that graph is below the x-axis? The part between negative 5 and 1. It should be between negative 5 and 1. It's below, correct? Okay. It's above the x-axis. Please pay attention. It's above the x-axis from negative 5 to negative infinity and positive 1 to positive infinity, right? Okay. You agreed with me, right? Between negative 1, I'm sorry, between negative 5 and 1, it was below the x-axis, correct? From negative 5 and 1, it's above. Okay. That means your graph is decreasing between negative 5 and 1, your original graph, and your graph is actually increasing from negative 5 to infinity and 1 to infinity. So wherever your first derivative graph is above the x-axis is where your original is increasing. And wherever your first derivative graph is below the x-axis is where your graph is decreasing. Thank you. Which is what we're going to go more detail in. Okay. So we're literally just finding the critical numbers, but I want you to realize why we are. So do critical numbers always give us max and mins? No, sometimes it gives us something else. It could be a turning point. It could be an asymptote of some sort, okay? So we're going to figure out how to be able to tell that, but not today. We're literally just doing critical numbers today. So with your first derivative graph, and we're only looking at that one, it's below the x-axis between negative 5 and 1, correct? Now, if you typed back in your original graph, you'd see that your original graph is actually decreasing between negative 5 and 1. The slope of your original graph is decreasing between negative 5 and 1. The cubic function, right? It's going like this. It's increasing to negative 5. It's decreasing between negative 5 and 1. And then it's increasing again, right? And your first derivative tells you that because wherever the first derivative is below the x-axis is actually where the original is decreasing. And where your first derivative is above the x-axis where your... But we'll be doing that with charts, right? You guys are just looking at it. But sometimes profs will give you a graph of a first derivative and ask you, what does it tell me? What does this first derivative graph tell you? The first derivative graph tells you that wherever it has x-intercepts are critical numbers, right? And wherever it's below the x-axis, the original graph is decreasing. And where it's above the x-axis, the original graph is increasing. All right. So you guys try and find the critical numbers of this one. I labeled that one A. Obviously, they're not all going to stay polynomials. If you actually given polynomials the whole time, life would be super, super fantastic. So when we do the derivative of this one, you're going to get f prime of x equals 6x squared plus 2x plus 2. Quiet, please. Take a 2 out, and you're left with 3x squared plus x plus 1. Now, we know we can't factor that, so a is 3, b is 1, c is 1. Now, before you used to maybe plug it in your calculator and then just see if it was above or completely below the x-axis, because if it was, then it wouldn't work in quadratic formula. But you don't have that option because you don't have your calculators. So we're going to plug it in. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So you're going to get x equals negative 1 plus or minus the square root of 1 minus 12 over 6. So it equals negative 1 plus or minus the square root of negative 12 over 6. Can we take the square root of a negative number? 11. Can we take the square root of a negative number? Absolutely not. Now, if you actually looked at your graph in your calculator, it's a cubic function. Now, in polynomials in grade 12, I have so many people fight me on this. So, your graph looks something like this. What is this? Okay, but what's it called? A point of? So it has a multiple C3, a point of inflection. So people fight me on it. It's where the graph inflects. It's called a point of inflection. When it touches and bounces back down, it's a point of tangency. This is a point of inflection. It's a point of inflection. It's neither a max nor a min. It's a point of inflection. It's where the graph inflects. Okay, it's a point of inflection. It's neither a max nor a min. People fight me on this. They're like, it turns. It's a turning point. It's a max or min. It's neither. And remember, critical numbers are your max or your min. This isn't one. But when we do the second derivative, which we'll do soon, the second derivative, critical numbers, will give us a point of inflection. And that's where we're going to actually see this critical number come up. But we're not going to see it come up here. So there are no critical numbers. So there are no max or mins or any other changing points. But it is still a cubic function. So if you get a cubic function, like we have, and there's no critical numbers in the first derivative, that's a huge, huge telltale that it's going to be a point of inflection, right? Because that means there's no maxes or mins. Because you're not going to get any critical numbers in your first derivative. And if you don't get any critical numbers in your first derivative, that means there's no max nor mins. You have to be able to solve them. This one you can't. It's a negative under the square root. So if you actually put this derivative, everyone please listen. What's this graph doing from left to right? Is it increasing or decreasing? Increasing. So your entire first derivative is going to be what? Above the x-axis. Because your first derivative, remember I told you your first derivative, any part of your first derivative that's below the x-axis says that the graph is decreasing, the original graph is decreasing between those values. Any part of the first derivative that's above the x-axis means it's increasing between those values, right? This entire first derivative is above the x-axis, which means the entire original graph is increasing. Wherever your first derivative is above the x-axis is where your original graph is increasing, right? This entire first derivative is above the x-axis. I really wish I could have my calculator working. It's just it's so much nice. I'll get it working tomorrow. Okay. Now they don't all stay polynomials. So C. Find the critical numbers of f of x equals x to the 3/5 times 4 minus x. Because this is a monomial times a binomial, there's two ways we could do this. We could do this product rule, or what could we do first? Which we could do this if it's a binomial times binomial. Distribute, and then do what? Power rule. Either ways, you're going to get have common denominators. So try it out, whichever way you want. You can either distribute and do power rule, or you can do product rule. Up to you. I'm going to distribute first. So I'm going to go f of x equals 4x to the 3/5 minus x to the 3/5 times x to the 1. What do we do when we have same base? Add exponents. So we need to make a common denominators in order to even add exponents. This is x to the 1 or x to the 5/5. It's supposed to be this exponent. It just looks like it's outside the bracket. Okay, so x to the 3/5 times x to the 5/5 is x to the 8/5. Then we're going to do the derivative because we haven't done anything yet. So f prime of x equals 4 times 3/5. X, drop it down by 1. So 3/5 minus 5/5 is negative 2/5. Minus, drop the 8/5 in front, x to the 3/5. Okay, then I have 12 over 5, and I have to move this to the bottom, make it positive, x to the 2/5. Minus 8, x to the 3/5 over 5. In order to get critical numbers, just like in order to do proofs and any of that other stuff that we've done in all of grade 12, we have to get a common denominator. We have to get everything over everything on the top over everything on the bottom. You can't have partial fractions and try and find critical numbers. Yeah. You could leave the x to the 2/5 on top as long as you take a GCF of the largest negative out, like we did before. That would work as well. Yep, that will work as well. Depends on the person. Because we did so many x to the negative 2/5, some people will find that way easier. Up to you. I'll do both. So up here, we would have 12 over 5 x to the negative 2/5 minus 8 over 5 x to the 3/5. You could take out your x to the negative. I'm just showing you another way. You can pull out a 1/5 x to the negative 2/5. Here, I'll do a common denominator on the other one. And then you're going to be left with 12 minus 8x. Correct? So there's your one way that you can have an answer by taking the negative out, which is what I pushed extremely hard in derivatives. So if you went that way, that's good. If not, you could have gotten a common denominator as well. You could times this by x to the 2/5 and this by x to the 2/5. And you're going to get 12 minus 8. X to the 3/5 times x to the 2/5 is x to the 5/5, which is just x over 5 x to the 2/5, which is actually the exact same thing, correct? Because I could move that x to the negative 2/5 to the bottom. So this would be the same as 12 minus 8x. I don't know why I put in brackets. And then 5x to the 2/5. They're actually the exact same answer. Now the numerator and the denominator give you critical numbers. Okay? So I always say to everyone, in the top, you could take a GCF out, right? You could take out a 4, and you'd be left with 3 minus 2x. The bottom, you actually have a 5 in front, and then an x to the 2/5. Now, what I've told you before, are these GCFs, do they get you any type of critical number if the GCF is just a whole number or even a fraction? If it doesn't have a variable, will it get you a critical number? That's you? No. The only way you get critical numbers is if there's a variable. Okay? So I don't have to do, I could go off to the side and go 4 equals 0 and say, wait, no, it doesn't. Okay, out, because we set it equal to 0. And then I could go 5 equals, wait, no, it doesn't. So I could prove that they'd give me nothing. Or you can just go by, hey, they don't have variables, they give me nothing. Your options. So then we have 3 minus 2x equals 0. And then we have x to the 2/5 equals 0. Now, here we'd get negative 2x equals negative 3, divided by negative 2, x equals 3/2. And then 2/5. We use this a lot in exponent laws in grade 12. How do we get rid of an x to the 2/5? Anyone remember? Raise it to the exponent of its reciprocal. No. So we are ultimately trying to get x to the 1. That's how we solve all of these, right? They're x to the power of 1. So how can I make x to the 2/5 to the power of 1? Well, I can raise this side to the 5/2, which means I have to also raise the 0 to the 5/2 as well, because what I do to one side, I have to do the other. What's 2/5 times 5/2? 1. So you can get x equals 0, because 0 to the 5/2 is just 0. So those are our two critical numbers. So what do they mean in this graph? Well, type the original in. Look for when x equals 1.5 and when x equals 0. No, because that would get you x to the negative 1. If you used this one, then you do negative 5/2, yeah, and it would get you 0 still. I just used the one where it was moved to the bottom, Mackenzie. All right. So we have 0 and 3/2. When you punch the original into your calculator, this one's actually a maximum. At 0, we have this little switch, and it's actually a vertical tangent running through it. So they don't always, the critical numbers aren't always just for maxes and mins. They sometimes will show you a point of inflection. It's not an asymptote, it's like a change in the graph. It's whenever there's a change in the graph in some sort, so it could be going from positive, negative to negative. The way you're going to know is we're going to do a chart, or if you had a sketch of the graph, you're going to see, hey, if it's going from positive to positive, then the graph just went like this, positive to slope to positive slope, so it would be an inflection. Or if it went from positive slope to negative slope, what happens when you go from a positive slope to a negative slope? You get a maximum. So we're going to look at that. But right now, all we're doing is literally just finding critical numbers, practicing that, so that when we add the chart, it's not so hard. Okay? So try this example. Still just finding critical numbers. X to the third minus x to the negative 2/3. One sec. What's that? Oh no, it's not a side of the room. That'll be fine. Okay, So you're going to get 1/3 x to the negative 2/3. And then you can get negative 2/3 times negative 1. So you actually get positive x to the negative 5/3. So they're actually both negative. So which one is bigger? Which one's bigger negatively? Sorry. You have pulled the smallest one, but it's the biggest number. So which is it? Yeah. It's there. I have no idea what you're talking about. So 1/3 x to the negative 5/3. And then we get 1/3 out. Negative 5/3. So x to the negative 2/3 minus 5/3 is 3/3. So it's 1. Remember, it always works out that way. It's so nice. So x to the 1, and then plus 2. Bam. So the catch here is x to the negative 5/3 equals 0. It's always going to equal 0. So if we just have x to any number like 2/3, 5/3, 1/3, 7, 8, what's it going to be always? Just 0, right? Because to get rid of this exponent, I'm going to multiply by this by an exponent, which means I'm going to multiply a 0 by an exponent. And 0 times any exponent is what? 0. So if we do this actually mathematically correct, we're going to raise it to the power of negative 3/5, which makes it still be 0. And then x plus 2 equals 0, x equals negative 2. All right. I'm not going anywhere. You want me to physically back up? I get it. I thought you meant like back up. All right. Oh, D. Do not whine. Okay, E. Do not whine. I'm warning you. No whining. So, when we do the derivative of this bad boy, we're going to get, come on. You're going to get g prime of x. The derivative of 4x is 4. Yeah. The derivative of negative tan x is negative secant squared x. Then I told you to get the critical numbers, you're going to set it equal to 0. So we have 0 equals 4 minus secant squared x. This you can do two ways. I'm going to show both because I do not care which way you pick. One way, you can literally solve for secant. So we move the 4 over. Negative 4 equals negative secant squared x. It depends on what person's brain goes to. Some instantly go to difference of squares and some instantly go to solving, so it doesn't matter. They're both very similar. So then we're going to divide by negative 1, and you get 4 equals secant squared x. Then you take the square root, but when you take the square root, you have to remember what? Plus or minus. So you're going to get plus or minus 2 equals secant x, which we'll deal with in a second. The other way that some people do it is they spot that this is a difference of squares. So they're going to put a 2 in the front of each bracket because the square root of 4 is 2. Square root of secant squared x is secant x. Then plus or minus. So when I solve them out, I get 2 minus secant x equals 0. 2 plus secant x equals 0. And I get secant x equals 2. And secant x equals negative 2. It's whatever, honestly, it would be a fight between people because it's whatever way that they just instantly see doing it. It doesn't matter, neither is more correct. So, the catch though, is that from trig in grade 12, you can flip an answer, but you cannot flip an angle. So if it was like secant of 60, let's say, you'd have to find 1 over cos of 60, right? But if it's secant of 2, that's the same as cos of 1/2. Because you can flip your answer. Now, cos equals 1/2. Oh, come on. At every 60-degree reference angle. Oh, yes. Or every because I just had a cumulative exam for 30-1. So, now, going back. Let's bring our brain back. We'll do degrees first because everyone likes degrees better, and then we'll just do radians after. So this is 60. And remember, the unit circle is not on your prof's wall. It never will be. You're not going to like go to your prof's room and there'll be a unit circle on the wall. It doesn't happen in university. Make you cover it up. You just be an idiot with a tattoo of a unit circle. Covered up. The right? I would actually just feel sorry for you. That's it. Okay. So, unless I restrict the domain of your graph, you're going to have to give me what? Starts with G, rhymes with general solutions. General solutions. Woo, okay. We cannot write all of these answers as one general solution. We cannot write all of these answers as one general solution, but we can write the ones across from each other as one. So I can write this one and this one together because they're just how many apart? 180. So I can start with my first positive one, and I can go 60 degrees plus 180 degrees NEI. And then I can put the next one, which is 120. I can put that. So I'm going to go 120 degrees plus 180 degrees NEI. But we're going to have our answers in radians. So 60 is pi over 3. 180 is pi. So we're going to go. Whoa, I don't even know where I'm going. My brain just stopped for a second. Okay. Theta equals pi over 3 plus pi n NEI. Or theta equals 2 pi over 3 plus pi n NEI. Fun, right? I know. Okay, we have one more example. Because what would math be without a lawn? You know? It would be sad. No. So, a rock yard, right? F of x equals x to the negative 2 ln x. Now, if I don't put this in brackets, a whole bunch of people try and do power rule for some sort. Like it's got to be a better way. No, it's product rule. You have to do product rule. What's the derivative of ln x? 1 over x. If it was ln x squared, then it would be 2x over x squared, right? Remember, you take the derivative of it right on top and rewrite it on the bottom. So the derivative of ln x is 1 over x. So we're going to do this one together. So f prime of x, we do f, which is x to the negative 2, times g prime, the derivative of ln x is 1 over x, plus g, which is ln x, times the derivative of f prime, which is negative 2x to the negative 3. Now, if we combine x to the negative 2 times 1 over x, what is it actually? x to the negative 3. Minus 2x to the negative 3 ln x. What can I take out of them? Yes. When I take an x to the negative 3 out of x to the negative 3, what do I get? Yes. Yes. 1 minus 2 ln x. Now that's fantastic, but you have to set them equal to 0 and solve. It's not as bad as it looks. Okay. So we're going to go x to the negative 3 equals 0, which we would raise that to the power of negative a third, and x would equal 0. It doesn't matter. It's going to get your critical number either way. The 1/3 would still be 0. Okay. Then we have 1 minus 2 ln x equals 0. Then we get negative 2 ln x equals negative 1. Then we divide by negative 2. Doesn't matter. And we get ln x equals a half. How do we solve ln? Ln is what base? Log base? E. Log itself is log base 10. Ln is log base E. Yes. Log base e to the x equals a half. And then we just do our 7 rule. E to the exponent of a half equals x. E to the power of a half equals x. And you have your critical numbers. To get rid of negative 3, you raise it to its reciprocal, which is negative a third. Because 3 times a third is 1. What you do to one side, you have to do the other side. Yes, but if you're actually showing the math, that's how you show the math.